Do you remember way back in 2019, we got the first ever image of a black hole, the supermassive black hole at the center of the galaxy Messier 87, all thanks to the Event Horizon Telescope. And then back in 2022, they also published an image of the supermassive black hole at the center of our own galaxy, at the center of the Milky Way, known as Sagittarius A star. And those images of those two black holes look slightly different because the Milky Way's black hole is much lighter in mass and therefore smaller in diameter, so you see more changes in the time that you observe it. I've spoken about this in a video before, which I'll link down below. And the Event Horizon Telescope team over the past 5 years have published so many papers explaining in excruciating detail how they took the data, why there were gaps missing in their data, and how they use machine learning algorithms to fill in those gaps. Plus, they've given a load of seminars and colloquium to fellow academics, fellow researchers studying the same topic, and also given loads of public talks to explain to the public what they've done to get these images as well. But this month, a team of researchers based in Japan, Miyoshi, Kato, and Makino, have released a paper that claims that using the exact same data from the Event Horizon Telescope that's been made public, they can't reproduce an image of the Milky Way's black hole that has a ring-like structure, so has that giant bright orange donut that's become iconic in these images. Instead, they get something that looks a little bit different, that looks more like a blob shape. But this isn't the first that we've heard from this research team in Japan. Back in 2022, they also published a paper that claimed the same thing for the Messier 87 data taken by the Event Horizon Telescope. Basically, this Japanese research team are claiming that these images, the ones that the Event Horizon Telescope collaboration released of Messier 87 supermassive black hole and the Milky Way supermassive black hole, are wrong. Now, the Event Horizon Telescope collaboration have also responded, first back in 2022 and much more recently this month as well in 2024. And they've stated that they think the Japanese research team's claims are wrong in themselves and they've misunderstood the Event Horizon Telescope data and also how you're supposed to analyze that data as well. So there is a lot to unpack here, and this video is going to cover a lot of ground. Starting first with a quick recap on what you're seeing in these black hole images, then how the Event Horizon Telescope works and how these images are constructed. Third, what Miyoshi, Kato, and Makino are claiming is wrong with the images. And fourth, what the Event Horizon Telescope team's response was and where that leaves us. I wanted to make this video because so many of you reached out to me when you saw that this research was covered in the news. Because with so many pseudoscience claims about how these black hole images are fake circling the internet, how do you know that a news story covering this research by Miyoshi and collaborators is actually reliable when it has a headline like "Astronomers throw shade at image of supermassive black hole in center of Milky Way"? That's where this week's video sponsor Ground News comes in. They're helping people like me and you to separate science fiction from facts in news coverage. Thanks to Ground News, I can see that this research was covered by 21 different sources, and I can compare the different language used by those sources, with some erring on the side of caution, saying that it might be wrong or not accurate claim scientists, but also with another claiming outright that we don't see reality in the images. But crucially for science news coverage like this, Ground News goes a step further by providing a factuality rating for each news source, so I can determine whether the description of the science in a given article is likely to be accurate or not. Ground News is the brainchild of ex-NASA engineer Harleen Kaur, and she's created this app and website that lets me cross-check facts across sources worldwide, which I find is so crucial if I'm reading about something that's outside of my area of expertise, whether it be climate change research or medical research. I think by far their best feature is their blind spot feed, where you can see which stories had little to no reporting on either side of the political spectrum, so I can find news that otherwise I might be missing due to my own biases, which as scientists we're always trying to challenge and eliminate wherever we can. So if you head to the link in the description down below, ground.news/Dr. Becky, or you scan the QR code, you'll get access to their increased discount of 50% off their Vantage plan, which gives you unlimited access to all of their features. It comes out to around about $5 a month, but that's only available for a limited time. Plus, by subscribing to Ground News, you are directly supporting my channel so I can continue to bring you more in-depth science content. So a big thanks to Ground News for sponsoring this video. And now let's dive into this and start first with a quick recap on what you're seeing in these famous black hole images. Because you might be wondering, well, how on earth do they take an image of a black hole? Something that by definition is so massive in such a small space, that it's so dense, that the gravity is so strong that nothing can escape unless it's traveling faster than the speed of light. But Einstein's theory of special relativity tells us that nothing can travel faster than the speed of light. It is a universal speed limit, and therefore nothing can escape a black hole, and everything is trapped there, including light itself, so that we can't see it. But what you can see is the light from the material that is orbiting around the black hole. And this is what they've taken an image of using radio light. So really low energy light with really long wavelengths. And the reason we can see it is because the black hole's gravity has accelerated that material up to huge high speeds, like close to the speed of light, so much that it heats up due to friction and then it emits light. So that's the orange donut in the iconic image, but you've also got this patch of black in the middle where there's no light detected. That is the shadow of what we call the event horizon, that point of no return around the black hole. I say point, but really it is like a sphere around whatever's inside it, which we don't know because we can't get any information or light from it because of this event horizon. It's the point where you'd have to be traveling faster than the speed of light to escape the black hole, which nothing can. And so together, this bright big ring of radio light and the shadow in the middle make up the images of these two supermassive black holes. One in the nearby galaxy Messier 87, that's around about 6.5 billion times the mass of the sun. That was first published in 2019. And then another of the supermassive black hole in the center of our galaxy, the Milky Way, known as Sagittarius A star, that's around about 4 million times the mass of the sun, that was first published back in 2022. And it's worth saying right now, as you look at these images, they are in radio light. So the colors don't mean anything, right? They could have picked any way to color this image. All you're really seeing is like where there is more light and where there is less light. That's really kind of hard for the human eye to really pick out with just a black and white image. So radio images tend to be colored this sort of like orangey color scheme, where you go from black where there's no light through orange where there's less light, and then white where there is the most light. So now you know what you're seeing, let's chat about how the Event Horizon Telescope actually works and how these images are constructed. So to do this, you need a really big telescope. And the Event Horizon Telescope essentially combines a whole bunch of telescopes that are scattered around the world to effectively create a telescope that is the size of the Earth. Because the bigger the telescope you have, the smaller the thing that you can make out on the sky. Like you'll have a higher resolution, right? You can zoom in more. So even though the Milky Way supermassive black hole is 4 million times the mass of the sun, the diameter of its event horizon, so that shadow in the middle that you're trying to resolve, right, where you're not getting any more light from those regions, that diameter is only around about the size of Mercury's orbit, which is like 160 million kilometers. But then the center of the Milky Way is 27,000 light years away. So it's a pretty small thing seen at a great distance. So you need a really big telescope to resolve this, because in terms of like how big this thing is on the sky, if you imagine that the sky is like, 360 degrees all the way around, then the Milky Way's black hole's event horizon only spans 0.0000001 degrees. So to actually detect this thing, you need a telescope that's the size of the Earth, which we can't build, so you have to combine lots of different telescopes from around the world in a process known as interferometry. You can think of this as if the Earth is a disco ball, with each bit of mirror of the disco ball a telescope looking up at the sky to see this one big image. Now, unfortunately, we don't have a giant radio telescope at every single little disco ball mirror segment on the Earth's surface, which means there are gaps in your telescope. But as the Earth rotates, this actually fills in some of the gaps in your telescope, in your disco ball, But as you can see, it's not all of the gaps that get filled in, which means there's gaps in your data, in your image that you're taking. So what the Event Horizon Telescope team did was develop a machine learning algorithm, an AI algorithm, that could be trained on all the other images that humans have ever taken, whether that's everyday images here on Earth, or whether it's astronomy images, or whether it's even simulations of what people thought black holes might look like, and then use that algorithm to say, okay, I've got these gaps in my data, what do I expect those gaps to look like based on the other data that I've already collected? Katie Buhlman, who's a computer scientist on the Event Horizon Telescope team, has given a great TED talk on this before. If you want to know more about how this algorithm actually works, I'll link it in the video description down below. So now you know what you're looking at and you know how the images were made. Let's get on to part 3. What this new study by Miyoshi, Kato, and Makino are claiming is wrong with the black hole images. So what this new study did was take the raw data from the Event Horizon Telescope that's been made public, you can grab it too if you want to, reanalyze the data themselves and see if they could recreate something that looked like the image that the Event Horizon Telescope team released back in 2022. The same research group did the same thing for the Messier 87 data from the Event Horizon Telescope back in 2022 as well. And both papers ended up concluding the same thing, that they couldn't recreate an image that looked like what the Event Horizon Telescope team had released either back in 2019 or in 2022. They couldn't recreate something that had this donut structure, this ring-like structure. Instead, they get something that is a bit more just like a blob in structure. They haven't resolved the Event Horizon shadow. And remember what I said before, this is radio light, this isn't visible light, so the colors don't mean anything here, right? They've just used a different color scheme to represent the data, but if you wanted to, you could take this same data and color it with the same color scheme of black, orange, and white, just like the Event Horizon Telescope images do, if you want to sort of like more directly compare them. Now, because they found this blob-like shape in the image, what Miyoshi and collaborators are claiming is that essentially they don't think the Event Horizon Telescope is big enough. It doesn't have a high enough resolution to resolve this event horizon shadow. And instead, the ring-like structure, what the Event Horizon team found for both Messier 87 and the Milky Way's supermassive black hole, is just an artifact. They're claiming that it's not really there in the raw data. And that's because they say, if you look at it, the Event Horizon Telescope's size of the ring that they found is the same size as something in what's known as the point spread function, or the amount that the telescope blurs something. So when you observe something with a telescope, right, you're passing light through lenses or you're reflecting things off mirrors, and that changes the shape of things that you're observing. So it takes single points of light and sort of smears it out a little bit and makes it into more of a blobbish shape. With a visible light telescope, that's essentially a slightly smeared out blob in the center, but it's also surrounded by fainter fringes around the outside in a pattern that's known as an airy disk. Now, as astronomers, we understand this really well. This is our bread and butter. It's why people could predict the shape that stars would eventually take, point sources of light, in JWST images like way before it's launched, because of the fact that it has hexagonal mirrors that are in a mosaic, and it has these struts holding up the mirrors as well that also affect the light as it comes into the telescope. With a radio interferometer telescope, right, where you're taking lots of telescopes and combining them and imagining the Earth like a big disco ball, right, you've got different distances between those telescopes. Those telescopes themselves are also different sizes. You've got lots of gaps in the disco ball array as well. That makes your point spread function, your PSF, a lot more complicated. And the PSF you get out by Fourier transforming the UV coverage has a lot more features in it. So straight away, any raw image you get out of a radio interferometry telescope where you've got all these dishes combined is going to be the shape of whatever you're observing convolved with the messy shape of this point spread function, so the response of the telescope to light coming in. This gives what's known as the dirty image in radio interferometry, and these dirty images are cleaned to remove the artifacts that come from the PSF that aren't real, and those dirty images are then cleaned up in the analysis, right? You account for all of these artifacts from the PSF. what's known as deconvolving for the PSF to get back at what is the shape of the object that I have been observing. So here's the PSF and the dirty map that Miyoshi, Kato, and Makino present in their paper. What they've done to get the dirty map on the right-hand side is just presume that you're observing something that is a single point source of light. And what you get out is something that has a bright blob in the center, that's the red bit. Then around that you have some areas where there's been less light detected, that's the blue bits, and then again a brighter bit, the red bits further out. And what they're saying is that the distance between those two outside red bits in this point spread function is the same size as the ring found in the original Event Horizon Telescope images. Which they stress means that if in your machine learning algorithm you then have something to train the machine that has this ring-like structure, you can then fill in the gaps to make this ring-like structure that isn't actually there in the raw data. And so what Miyoshi and collaborators are claiming is that even if you've observed something that is blob-like in shape because of this PSF, and if your machine learning algorithm is trained on things that have ring-like structures in the images, then you can produce an image at the end that has this donut or ring-like structure. So with all of that said by Miyoshi and collaborators, what then was the Event Horizon Telescope team's response? Well, back in June 2022, 6 weeks after that first Miyoshi and collaborators paper was published about the Messier 87 data, the Event Horizon Telescope team put this blog up on their website. And they first reiterated that they welcome anyone to grab their raw data and do independent analyses to confirm what they found, because that is a really crucial part of scientific research, right? Reproducibility, making sure that other people can reproduce what you've done and find the same thing and confirm your results. So the Event Horizon Telescope team have not just made like the data they've taken public, but also all of the analysis code and the machine learning algorithm they've used. They've made all of that public as well. Then they get on to commenting on the study first published by Miyoshi and collaborators in 2022 and state that our team has determined that this new reanalysis by Miyoshi and collaborators is based on a flawed understanding of Event Horizon Telescope collaboration data and its methods, leading to erroneous conclusions. Essentially, they said, we don't believe Miyoshi, Kato, and Makino's claims, but they didn't exactly give a lot of detail as to why not. That led to yet another rebuttal 6 weeks later, again with this article appearing online from Miyoshi, Kato, and Makino, challenging this claim that the EHT team made that their understanding of the EHT data and methods is flawed. And they asked the EHT team to clarify what they meant and provide more detail. And then all was quiet for a while. I did find this line in a paper from the EHT team in 2024. It's in amongst a paragraph that discusses all the independent analysis that have been done to verify their work, and then at the end it just says, there is another external analysis of the 2017 data that claims not to support the EHT interpretation, and it cites the Miyoshi 2022 paper. That was the last thing we heard until Miyoshi, Kato, and Makino published this paper about the Sagittarius A star data, the Milky Way's supermassive black hole, earlier this month. But as I was prepping this video, we then heard from the Event Horizon Telescope collaboration, again on a blog on their website that was posted on the 29th of October 2024, with a whole load more detail this time. Now, if we're entering the realms of speculation here, this is just my thoughts. I reckon they had this text to put in the blog post with way more detail, probably because they've been working on a proper research paper to publish to rebut all of Miyoshi and collaborators' claims. Now, that research paper will be taking a hell of a long time because, first of all, they have to be very, very careful with their analysis and be very sure with what they're claiming, so they'll be doing, a lot of rigorous work. But also, anything that gets written is going to have to get sign-off from every high-up person in the collaboration, which will take a lot of time in itself as well. I don't know that for sure, that's just my guess, but I think this is why we got more detail this time. So first, they list all the things that they think are wrong with the analysis in the latest Miyoshi paper, from not taking into account the variability of the Milky Way's black hole and not using the full suite of imaging data that's available, just data from one night. And then they list the things that Miyoshi and collaborators stated wrong about how the Event Horizon Telescope collaboration even did things in their analysis. Now, they go into a load more detail about each of those bullet points later on in the blog post, but I think the key thing to highlight here is this point spread function issue, this PSF issue, where they say, of course, they correct for the PSF shape in their analysis, just at a different point in the process than Miyoshi and collaborators do. Plus, the Event Horizon Telescope team has also looked at the polarization of the light around these black holes as well, sort of like the orientation of it. It's what produced the sort of croissant rather than a donut image, as I like to call it. And when they look at the polarization data and use the exact same algorithms that they used to produce the black hole images that they first released, they produce something that is blob-like and not ring-like. So they don't think the algorithms are erroneously producing rings that aren't there due to the PSF. The Event Horizon Telescope team claim that this ring-like structure appears no matter what you assume for the shape of the object that you're observing. Look, I'm going to post the links to all of these papers and the blog posts below so that you can read them for yourselves if you like. Because one of the reasons I made this video is because I thought you'd all really enjoy sort of seeing this discussion between two research groups play out in real time. And I know that many of you in the comments are going to be asking, but what do you think, Becky? Who do you think is right? And the thing is, while this is my research field in terms of black holes, it is definitely not my research field when it comes to radio astronomy. I am a visible light astronomer. I use telescopes that look in, visible light, maybe some infrared, maybe some UV. I'm familiar with things like spectra and data cubes and proper images. I am not an expert when it comes to this process of interferometry, this combining different telescopes from around the world into one big giant telescope and all of the headaches and nuances that come with that. So I can only read what both research teams have said they've done and just take that at face value that they think they've done the correct thing without actually having any intuition myself for what the correct thing is. If you're going to make me decide, then look, my intuition is that the Event Horizon Telescope collaboration is a huge number of radio interferometry experts and computer scientists, with over 300 people worldwide working on this, who thought for so many years on not just how to do this, but the best way to do this, and thought about that, before, during, and after taking their data. And I think they will know their data the best. And so I'm inclined just to lean ever so slightly over the Event Horizon Telescope collaboration side of the fence. But this is why science relies on having a lot of experts on these different techniques of radio interferometry that, work in different collaborations in different institutions worldwide that can look at both sides of this argument and then comment on, which way they think is the correct way to do this and get a general agreement from the field. That with time, slowly but surely, time for careful science, that means the rest of us non-experts in that specific technique in the field of astronomy, and also by extension, the general public over time as well, can get a much better understanding of which are the more accurate images of these two iconic black holes. So I just filmed the entire intro without turning the microphone on, which was very clever. Let me check the levels are right. Yeah. At least it was only the intro. The other day I did it for the entire video. And also, I really need to stop filming right before lunch because my belly is grumbling so much. It's in under gravity. Maybe my brain just wanted to say mavity still. Someone's going out the front door and I don't know if it's going to pick up on the camera, so. We've got family here. Let's use this as an excuse to put some lip balm on. I am so hungry. I am gonna go absolutely smash my lunch.